New findings about magnetic field lines and the direct observation of their reconnection in space have started to give scientists hope that they can find a way to access fusion power as an energy source. Here's everything we know about how magnets could be the missing link for long-term space travel, and how scientists are making oxygen for long trips. First off, why we need more oxygen. Making enough oxygen for astronauts to breathe in space is a tricky affair, but that is only set to become tougher as we venture to Mars and probably even beyond. Now, researchers have found a brand new method of making oxygen for astronauts using magnets, according to a statement by University of Warwick. On the International Space Station, oxygen is created through an electrolytic cell that cuts water into equal halves of hydrogen and oxygen. It doesn't end there. Then you have to pull those gases away from the system too before the oxygen can be used. It's not exactly a simple process. A fairly recent analysis from a researcher at NASA Ames drew the conclusion that taking on the same architecture for a trip to Mars would have such giant reliability issues and mass penalties that it would be dumb to go through with it, according to a leading author who's been doing extensive research on the subject, Alvaro Romero Calvo. What NASA is currently doing is using centrifuges to get oxygen in space. But let's not forget just how big and how high maintenance these machines are. As for the new research, practical experiments were conducted, which displayed how magnets could bring us the same results much more easily and practically. Moving on, how the tests were conducted. These tests happened in the Center for Applied Space Technology and Microgravity, or ZARM for short, in Germany, at a specialized drop tower facility that kind of imitates microgravity conditions. After years of analytical and computational research, being able to use this amazing drop tower in Germany provided concrete proof that this concept will function in the zero-G space environment, was what Professor Hans-Peter Schaub had to say. They carried out the study by injecting air bubbles into syringes, which were filled with different carrier liquids. By doing this, the team used the power of magnetism to successfully detach gas bubbles in microgravity. This outcome was proof that the bubbles can be both repelled by and attracted to a neodymium magnet from within different substances. Besides that, the scientists discovered that through the inborn magnetic properties of different aqueous solutions they tested, such as olive oil and purified water, meaning it's totally possible to direct air bubbles to separate locations within the liquid. Essentially, this makes it much easier to send or collect air via a vessel. Besides just using these findings to create an abundance of oxygen for the space crew, Romero Calvo says that these results display how developing microgravity magnetic phase separators could lead to even more lightweight and reliable space systems. For example, more efficient wastewater recycling methods and propellant management devices. To demonstrate the magnet's possible use for research purposes, the team also experimented with lysogeny broth, a medium used to grow bacteria, for ISS experiments. Now for the results. They found that the olive oil and broth both were greatly affected by the magnetic force put on them. They also found that gas bubbles did both. They repelled and attracted. The researchers then devised a procedure to detach gas bubbles from electrode surfaces in special microgravity environments created specifically for 9.2S at the Bremen Drop Tower. The study proved for the very first time that gas bubbles can be repelled from and attracted to a simple neodymium magnet in microgravity. The difference is created by immersing them in different variants of an aqueous solution. Dr. Katarina Brinkert of the University of Warwick said that effective phase separation in lessened gravitational environments has been a challenge for human space exploration, which has been plaguing experts since the very first flights to space in the 1960s. This issue poses a special challenge for the life support system on board the International Space Station and spacecraft, since oxygen for the crew is generated in water electrolyzer systems and needs to be separated from the liquid electrolyte and electrode. It's not quite as simple as getting water when you're on Earth. Brinkert came to the conclusion that this new method could lead to big consequences for the future development of phase separation systems. For example, when it comes to long-term space missions. Next up, why can't we keep sending tanks to the station? Even though astronauts are usually sent off to space with ample stores of the needed supplies, it would be way too expensive to keep sending tanks of breathable air up to the station. Instead, the oxygen that astronauts depend on for their life is made through a process called electrolysis. This process is when electricity is used to split water into the two gases it's composed of, oxygen and hydrogen. Pretty much the same process happens naturally on Earth through photosynthesis, when plants take in hydrogen and use it to produce sugars for food and release oxygen into the atmosphere. Yet, because the system on the ISS needs an insane amount of upkeep and energy, scientists have been searching for alternative ways to sustainably make breathable air in space. For now, pulling gases from liquids through magnets is the best choice. Many people don't know that water and other liquids have magnetic qualities. The physical principle is pretty famous in the physics community, but applying it in space is another thing that has so far barely been explored. When a space engineer is mapping out a space system which involves fluids, they don't even stop to think of the possibility of using magnets to bring about the phase separation. Finally, where do we go from here? If the next generation of space engineers do decide to apply magnets to future space stations, the new method could generate more efficient, breathable atmospheres to support human travel to other places in outer space, including Mars and to the Moon. If we were to come up with a plan for a human mission to Mars, the ISS's present oxygenation system is too intricate to be properly reliable during the long trip. Making the whole process simpler with magnets would ensure there's plenty of oxygen with less costs. It's a win-win situation. V. Romero Calvo says their breakthrough could ultimately help humanity land on Mars. Other scientists are figuring out ways to make oxygen using plasma. Plasma is a state of matter that has free charged particles, such as electrons, which are easily excited by powerful electric fields, for fuels, fertilizers, and other materials that could help colonize the planet. And while neither project is on the level of execution just yet, these upcoming developments represent the spectacular feats humans have the potential for as we continue going forward, struggling to go where no man has before. Other related news. First off, why is it important that ISS recycles its air and water? As you might have guessed, storage is hard to come by aboard the International Space Station. Even if a rocket had the space to ferry thousands of pounds of water along with oxygen to aid a 6-month mission, you'd have a lot of trouble finding a place to stash it. So engineers have come up with innovative ways to squeeze out the essentials from astronauts' very own urine, sweat, and breath. But we haven't got to a total recovery yet. As of now, the ISS successfully recycles 90% of its water, which adds up to over 1,000 gallons annually, as well as 40% of the oxygen breathed by astronauts. The rest is taken care of on resupply missions. To put things into perspective, an Earth-bound human would take up about 80 gallons of water per day. On the other hand, an ISS resident will have to stretch just one for drinking, showering, just about everything else. Now, just how do they recycle water in space? Astronauts' bodies generate plenty of carbon dioxide and sweat droplets. Both of these get sucked into vents and are headed for recycling. When astronauts go number one, a lightweight vacuum in the toilet sucks urine into a low-pressure chamber, which makes the water evaporate. This gives you a salty brine, which is later jettisoned by resupply vehicles to burn up in the atmosphere. Water can actually carry out double duty if its atomic components detach from each other. An electrified membrane halves the molecules. Then, oxygen pumps into the cabin, while hydrogen goes to a specialized reactor, aka a Sabatier, to turn back into water again. In case you are wondering how this machine works, on the inside of it, a blast of roughly 750 degrees Fahrenheit heat tears the bonds with CO2, forcing it to turn back into its composing elements. The oxygen and carbon fuse with hydrogen from the station's oxygen generating system. This makes H2O and methane, CH4. The methane then vents off to space. Lastly, how this water is made safe for use. Reclaimed water then goes into a chamber chamber in the US lab module, where an OxyClean-like reaction clears it of any leftover smell and even kills bacteria, making the water safe to use. A shot of iodine then kills off any leftover germs, but it's routine among astronauts to test the water regularly just to make certain. That's a wrap for this video. Do you think these new discoveries are going to help us explore outer space and create oxygen easily? Let us know in the comments below. Subscribe to our channel for more videos like this. See you in the next one.